PVS is an interactive proof assistant for formalizing mathematical and computational content. Its specification language is based on higher order logic. Here we have a PVS file with a theory big num that formalizes big number arithmetic and big number numerals with respect to an arbitrary base. The base here is a parameter to the theory, and it has type above 1. That means it has to be at least 2. You can think of the base as either 2 or 10, for instance. And the body of the theory consists of a sequence of declarations of variables. Carry in, for example, is a variable of type up to 1. And so it could be 0 or 1. The type of digit is below base. So if the base is 10, then the digit can be anything from 0 to 9. And the typing judgment here says that 1 is always a digit for any base. This is used by the type checker automatically. The main type here is that of the big num numerals big num. And that's a list of digits in little endian order with variables x, y, and z ranging over big nums. The main part of the theory consists of 3 definitions. The first computes the value of a numeral x as a natural number, and it's a recursive definition that terminates with the ranking function length of x that decreases with each recursive call. The next definition is that of digit addition. You add a single digit I to a numeral x, and this too is a recursive definition that terminates with the ranking function length of x. And the third definition is big plus of x, y, and cn. It adds 2 numerals x and y together with a carry in. And there's a mistake in the definition where when you take the least significant digit of x, which is j, and the least significant digit of y, which is k, and add it to the carry in and compare it to the base, then you should be subtracting the base in the first instance with a carry of 1 for the recursive addition. Unfortunately, the 2 cases here are reversed. So this would be the problem out here. Now you can take a theory like this and you can type check it. And this generates a collection of proof obligations for demonstrating that terms are within their subtypes and the termination conditions actually hold. And then you can try and prove theorems of this kind, where you're proving that the value of the digit addition of I to x is equal to the value of x plus I, where the plus on the right-hand side is just the arithmetic plus. And this has the step induct and simplify on x, and that proves the theorem. And you can also try and prove the theorem with the bad definition, which is that the value of big plus of x, y, and cn is equal to the value of x plus the value of y plus cn itself. And again, we try and prove that, and that too has a proof induct and simplify. And this proves, even though we have a bad definition, it proves because though we have the cases reversed, we're careful to conserve value, and that's the reason it proves. But what is different about this is that the proof obligations, when you try and discharge them, you end up with unfinished proof obligations. And so the TCC3 and TCC5 no longer prove, and you can go back and fix the definition. You can swap the 2 cases and see if that fixes the problem. And then we can prove the entire theory now. And indeed, this proves everything. And then we can go back here and actually evaluate some of these expressions. So we can take an expression of this kind and evaluate it using PVS IO. So we enter it out here, and we get the right answer, 1840, for the addition out there. That's it.